Okay, so I'm going to do the classic example of what we mean by the correct skeletal structure. Okay, what do we mean by the correct skeletal structure? In a previous video, I said that's kind of a weird term. How could you know what's the correct skeletal structure if you're just learning how to do this? First of all, I'm going to start out. So this is Lewis dot structures examples. Correct skeletal structure. Okay. First example I'm going to do is, again, remember we're starting out with the molecular formula, and you're always going to get that in the question stem, the molecular formula, and then from that we're going to do the Lewis dot structure. Okay. The correct molecular formula for the one I'm going to start with this time is H2. This is not unusual for us to have. I'm going to do 3 examples. This is 2 maybe, but I'm going to do 3. H2. First thing we do is we write the correct skeletal structure for the molecule, okay? And we make a guess. What I said here was the correct skeletal structure. It means a structure that results in the best Lewis dot structure. What is the best? It's still an open question. And we start by guessing, and we default to symmetry. Okay, so if we're going to make a guess with hydrogen, there's only one possibility. And it's not unusual, by the way, to have a pretty simple molecule that you've got to evaluate. So let's start there. Pretty simple. There's only one possible guess. So the correct skeletal structure is obvious just because we try. Okay, so we make a guess. That's step number 1. Step number 2 is we calculate the total number of valence electrons. Okay, and the way that we calculate the total number of valence electrons is, the total valence is the number of electrons in the outer shells of all the constituent atoms. Okay, so the constituent atoms for this molecule are just H and H. Those have how many electrons in the outer shell? 1. So we're going to say it's 2 times 1, which of course equals 2. Alright, I say write it out. Always write it out. Now in this case it's so simple that that's not a very convincing argument that you need to do that. But you'd be surprised at how often I see incorrect answers, and this is where the problem is. And it's excruciating because it's such an easy step. People have a tendency to do it in their heads, which is a mistake. Write it out. This should be the easy part. Alright? So it's 2 electrons. Step number 3. We normally won't write it out like this, but just to keep things clear, I'm writing it out, okay? And we normally won't write each step, twice or 3 times. Now, assign the electrons. I've implied these 2 are next to each other. They're bonded. So let's write those electrons. I just wrote 2 electrons because it's a bond, and that takes us down to 0. Right? We have no more electrons to assign. So now I'm going to go left to right and evaluate every atom in here and see if it's good enough. This hydrogen has 2 electrons. How many electrons can hydrogen have in its outer shell? Only 2, so that's good. And this one also has 2 electrons, right? These are covalent electrons, and so that's also good. I realize this is such a simple example that it may you may be rolling your eyes and saying, what value is this? But watch, we're going to practice the steps, and we're going to find that if we practice the steps, there is no molecule that scares us. Okay? So this is good. We're done with H2. We're done with H2. And the Lewis structure is that. Okay? Let's do another one now. Let's say that we're going to do O2. And we need the Lewis structure for that. Okay? Remember, we start with the molecular formula. That's in the question stem. Molecular formula. And that goes to Lewis dot structure. Okay? O2. And the first thing we're going to do is we're going to assign all the atoms. There's only one possible place they can go, and that's right next to each other. Number 2, we're going to count the valence electrons. And that would be, there's 2 times the number of valence electrons in oxygen, which is what? 6. It's in group 6, right? So there are 12 electrons to assign. Step number 3, we're going to assign them. Right, remember, I should be taking you back to this card each time. Write the correct skeletal structure, which we did, right there, OO. Calculate the total number of valence electrons, which we did, 2 times 6. Number 3, assign the electrons in bonds and lone pairs. Okay? So, we've implied that these guys are bonded, so we're going to do that. and we're going to say our 12. We now have 10 more electrons to assign. Okay, so what I'm going to do is 2, 4, 6. I've just gotten rid of 6 more. I now have 4 more to assign. Right? 2, 4. Okay, I've now assigned all of them. Now I look at this, and it's not symmetric, first of all, so that bothers me. But secondly, I'm gonna go through and just look at everything and say, is the octet filled? 2, 4, 6, 8. That's good. Okay, 2, 4, 6. That's not good. Now it's time to look at step 4. Move the electrons. That is either bonds to lone pairs or lone pairs to bonds, so that we can satisfy the octet rule. Do consider double and triple bonds. Okay? So I can bring these electrons, because this one's the one that's short, right? So I've got to bring some electrons into it. So I can bring these electrons right here and that, put them there. Now be really careful. When you're moving electrons, I'm going to X them out so I don't have them twice. I think in the last, I'm going to go ahead and recount these electrons again and make sure I end up with 12. Okay? So this is better for a couple reasons. It's symmetric, and so I like it better. But there's a reason why, by the way. That's not just for aesthetics, okay? So usually symmetry is right, so we're going to default to symmetry. Your gut feeling on that's probably correct. But there's another reason why it's better, because we'll see. 2, 4, 6, 8. That's good. I already put a check mark, so I'm going to do that. 2, 4, 6, 8. That's also good. Okay, so we're good. That is the Lewis structure for oxygen. Boom, boom. Okay. All right, and the final one I want to do for this video, Lewis dot structures examples, we're really probing that first correct skeletal structure. We're probing that first step a little bit, saying what could that possibly mean, right? So this first time we did 2 diatomic ones. We did H2 and O2, where the correct skeletal structure was obvious. Now let's do another one. Let's do N2O. This is probably in every principles textbook because it's a classic example of this first rule, writing the correct skeletal structure. It's a classic example. And what I say in writing the correct skeletal structure is, I say, remember, this means a structure that results in the best Lewis dot structure. And we start by guessing default to symmetry. Okay? So, my first guess is N, O, and N, because that's symmetric. Right? That's step 1. Step 2 is count up all the valence electrons. That's a dot, right? It's not supposed to be an electron. Okay, that's a mistake. So there are 2 times nitrogen and 1 times oxygen. Nitrogen's in group 5, so there's 5 valence electrons. Oxygen's in group 6, so there's 6 there. This gives me 16 electrons, right, to assign. N, O, and N. I implied those 2 were bonded, so let's write those 4 electrons out right away. That gives us 12 more to assign. Now let's go through here and go 2, 4, 6. It gives me 6 more to assign. 2, 4. Notice I'm doing the lone pairs in there to give the octet rule, right? Just going up to 8 and stopping. Okay. 2, 4, and we have 2 more to assign. 2. Okay. Well, this is not symmetric, so I have a I'm scared of it, but it we'll still go through and evaluate it systematically. First of all, 2, 4, 6, 8. That's good. It's not good, okay, but it works. All right. What does good mean, right? 2, 4, 6, 8. That works. 2, 4. Uh-oh. Okay. Well, remember now, with the rules, we're going to assign the electrons, which we've just done. Now we move the electrons, either from bonds to lone pairs or lone pairs to bonds, to satisfy the octet rule. Don't forget, we can access double and triple bonds. Okay. So let's move these 2 outside the circle and into it. Get rid of them when I draw them so I don't have the wrong number of electrons on there, because the wrong number of electrons is a guaranteed wrong answer. Okay, so that's 2, 4, 6. That works. I'm sorry, that does not work for nitrogen still. Although this guy, let's start back from left to right. 2, 4, 6, 8. That's still good. 2, 4, 6, 8. That's still good. 2, 4, 6. All right, that's not good. But we can do 2 more electrons. Okay, make it a triple bond. Let's get rid of those there so we don't have the wrong number of electrons in there. Okay, 2, 4, 6, 8. That's good. All right. Now, we've moved the things around enough. I'm always scared at this point. I start all over again. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That's good. All right. This Lewis structure works. Okay, but the correct skeletal structure means a structure that results in the best Lewis dot structure. All right, it works, but we have a problem. Oxygen has 4 bonds, and this nitrogen only has 3. I'm sorry, only 1, and that nitrogen has 3. Definitely not symmetric. Excuse me, it's definitely not symmetric, and it is and oxygen has 4 bonds, which is a real problem. That's a problem which is going to be, we're going to probe a little bit later in something called formal charge. Okay? But for now, let's just say oxygen having 4 bonds is a problem. All right, let's try another structure though. So we tried the correct skeletal structure with a symmetric, and we don't like the answer. Let's try another one which is not symmetric. N, N, and O. That's the only other possible. I guess we'd have this in a triangle, but it's not going to be a triangle. It's going to be linear. Triangles are rare in chemistry. For now, don't do any triangles. That is 3-membered rings, right? We're talking about this. You don't want to do that. It's a 3-membered ring, and for now, we will have no 3-membered rings. All right? So let's try this. Step 1 is that. Step 2 is 16. 2, 4, 12. I'm just going to go ahead and do a double bond. 2, 4, 8 more. Okay. Okay. So now that we've got that, let's go through here and evaluate. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That's good. So the question is, why is this better than this? And the answer lies in formal charge. Again, that's a separate video. But this is the classic example that's given in every textbook. Well, I think every textbook is N2O, dinitrogen oxide. The example that's given for when the correct skeletal structure is not symmetric. Okay, there's only one other example I can think of, and we will be describing that in a future video. For the most part, when the correct skeletal structure almost always means a structure that results in the best Lewis dot structure. What does that mean? Well, here, start by this. You guess, and in your initial guess, default to symmetry.